Hello, everyone, and welcome to another episode of Mathematics for Computer Science and Artificial Intelligence. This is a very exciting video because in this one we finally tackle neural networks, or better said, artificial neural networks. So, we'll divide this series into three parts. So, for the first part, we're introducing some concepts of neural networks. We're going to compare the biological neural networks to the artificial neural networks, or rather, we're going to look at the biological neural networks and derive what some artificial neural networks would be like. And then we move on to bigger and more exciting things such as the mathematical modeling behind these artificial neural networks. So the first thing that we have to ask ourselves is, why do we even bother with artificial neural networks? Why do we even study them? Why do we develop them? And I think we can just begin by saying we've always been very interested in creating a computer capable of general artificial intelligence. So general artificial intelligence is also referred to as super artificial intelligence or strong artificial intelligence. These are beings that can pretty much learn anything, and they're programmed to have general intelligence, which means that they don't have to know how to do one task specifically. Rather, they can learn an array of tasks, and you don't have to program them to learn that array of tasks. Some people may even say that strong AI are beings that have consciousness. Well, that may be a different thing, but so I'm just mentioning it for purposes of completeness. So, if we want to create a being with general intelligence, well, we already know a being, and we know the smartest being that we know is actually ourselves. We have general intelligence. So, why don't we try to create a being that works in a similar way to how we work? So, what do? We try to imitate the human brain at a cellular level and try to create a mathematical model of the brain and embed that into a computer so that the computer could have a brain that functions like the human brain. And thus, we would, in theory, be able to create general artificial intelligence. Now, after all of these ideas, a new branch of artificial intelligence was born. So just as a chain explanation here, we have artificial intelligence. So inside of artificial intelligence, we have machine learning, which is pretty much teaching the computer to learn in a similar way to how we learn. But then inside of machine learning, there is another branch, which is deep learning. So deep learning is all about artificial neural networks. This is why we have artificial neural networks here. And this whole branch of trying to imitate the human brain is called neuroscience-inspired artificial intelligence, which means that we are taking the inspiration from our design and putting it into a computer so that we can build a computer that possesses human-like intelligence. So first, let's discuss biological neurons. So I'm just going to discuss it in images here because I think it's easier to understand. So this right here is a neuron. These are all neurons, but let's just focus on this one, right? So let's see what the parts of the neurons are. So right here we have the cell body. So this is the support center of the cell. This is also called the soma. Here we have the dendrites, right? So all these like little branches that are coming into the cell's body are called the dendrites. And then this long thing here is called the axon. So I'm just going to focus on the important ones, right? So we have the axon, which pretty much is used to pass messages away from the cell to other neurons. So these are the terminal of the axons. These are the terminals. So some message comes across through the axon and is passed through the terminal branches to other neurons or glands, as it say here, right? So neural impulse is pretty much because neural networks fire. And when they fire with some electrical potential, some electrical signal that travels from one neuron to other neurons or glands, right? So now, as you can see in the image down here below, this is like a network of biological neurons. And when they are connected, at the point that they're connected, so the terminals here of the axon connect to the dendrites of other neurons, and that's pretty much how they form like a chain of neurons. So again, the terminal of the axon connect to the dendrites of other neurons. So here, if we say that this is the terminal of the axon, then this would be a dendrite right here. And that's pretty much how neurons connect to one another. So the connection between the terminal of the axon or terminal branches of the axon and the dendrite is called a synapse or synapse. Some people pronounce it differently, but yeah. So let's call it the synapse, right? So that's the synapse. So now let's look at artificial neurons. In what ways are they similar to biological neurons? So I had a little fun around, and I pretty much created these photos to illustrate and compare them to biological neurons. So this is the neuron right here. This is like kind of like the body, right, or the soma, and these are like the outputs. This would be like the axon terminal. So they don't necessarily have one axon and then it has like different terminals or whatever. It's like well, as you can see, it's much simpler than the biological neuron. And because it is simpler, obviously it's not the exact same thing. And the reason why we don't create an exact neuron is because we don't know exactly how all neurons work and how they function. So we have to use our creativity and create something that's similar, even though it's simpler. So we have the outputs. In artificial intelligence terms, these are the outputs, which we'll later see that they're also weights. But these are the outputs, and when we look at it in terms of the biological neurons, this would be sort of like the axon terminals. So here, this would be like the dendrites, right, or the inputs. So these inputs might be the outputs from other neurons. So even though from the perspective of these neurons, these are the inputs, from the perspective of another neurons, this might be the outputs. So let's look at the network here. This is a network of artificial neurons. So we have a neuron here. It seems like the neuron is connected to several other neurons before, right? And then right here, there is a synapse or synapse, right? So these synapses are like the weights. And if you remember our multi-regression series, then you have some idea of what the weights are, right? So again, these weights connect neurons, and when they connect neurons, they can pretty much form a chain of neurons, or what we call a network of neurons, artificial neural networks, hence the name, right? So once again, these weights can have different these weights can be different amounts, right? So maybe the output of this particular neuron matters more or the output of this neuron matters more than the output to this neuron to the actual output of this neuron. Okay, so something else. We defined before how biological neurons actually fire, right? So they fire. In terms of artificial intelligence, we can call this they activate, or actually in terms of neuroscience also, a neuron can activate. So activation is formed in terms of previous neurons. So say, for example, somebody smells something, and then that smell comes into the human body and is processed. I'm not going to pretend to be an expert in neuroscience, but in simple terms, it's processing all this smell, and this smell triggers some neurons. So some neurons fire. And then this firing of these neurons connect to other parts of the human body and then produce a response or an output. So this is pretty much what we're trying to do here, the same thing, right? So we have some inputs, which in this case is not smell, right? We have some inputs, and then those inputs are propelled onto a neuron that may or may not fire. So now that we know this, let's move on a little and see how an artificial neural network actually looks like. So let's see. Let's look at the mathematical model behind it. And I'm not going to go too much in deep into the actual mathematical model in this video, but as we move on, I promise you that we will. So these are different neurons. So the circles represent the neurons. And as you can see, they're organized in layers. So now we have these little lines right here that connect the layers of neurons. These we refer to as the weights of the neurons. So these are also layers, and we have the input layer, which is the first layer of neurons. We have the output layer, and then we have the hidden layers. So the hidden layers are pretty much part of the network. So the hidden layers are part of the network, but the input is what is being passed to the neuron, and the output is what is being taken or received, the response that we receive from the neural network. So we don't really know what happens with the hidden layers, and this is why they're called hidden, because nobody really knows exactly what's happening within them. We know how they propagate, we know how they calculate their values, but we don't know exactly what features of the input these neurons are extracting. So they're called the hidden layers. And as we have many hidden layers, then we call this a deep neural network. Hence the name of the branch, deep learning. So we have deep neural networks, which are part of the bigger branch, deep learning. Right. So now, what does this mean, right? So they're organized in a layer structure, as I've already mentioned. So the values of previous neurons determine the values of subsequent neurons. So the value of this neuron right here is determined by the values of these neurons before. And so again, the value of this neuron is determined by the values of these previous neurons before. So again, the values of these neurons depends on the values of the previous neurons before. And I think you kind of get it, right? So finally, the output is computed or calculated, right? So the idea is that these input layers are passed in, and then these input layers propagate to this layer, and this layer is calculated, and this becomes sort of like a new input layer, and then they compute this layer right here, then this layer is propagated and computes this layer, and then this layer finally is propagated and computes this output layer, and then we get some output that is meaningful. So now, let's see. We have learned linear and multi-regression. And I promised you before that this will be important when it comes to neural network. And let's see how we can see them as a network of neurons, the linear and multi-regression. So let's see the equation of a line, right? So before we have y equals mx plus b, right? Okay, when we used our multi-regression, we replaced m by weight. So let's do the same here for the sake of simplicity. So instead of mx plus b, we have wx plus b, or the weight of this input plus the bias. And this is actually the same thing. It's just different representation, but conceptually it's the same thing, right? So how do we visualize this as a network of neurons? Okay, so we have an input. The input is x, right? And then we have a weight. The weight is represented by this line right here. So this weight is then used to compute the output. But to this output, to this xw or wx, we have b that we add on top of it. So this is like a very simple network of two neurons. So we have one input neuron and one output neuron. And that's actually the simplest way of looking at a neural network, right? Now let's look at a multi-regression. So again, a multi-regression has multiple inputs and only one bias, but then also one output. Only one output. So in this particular case, we're considering a multi-regression or a multi-input equation with only two weights. So two weights here, which means that we have two input neurons. So we have x0 and x1. These are our two input neurons. But then again, we have also two weights. We have two weights. And these two weights with the two inputs and the bias are used to compute the output. So again, this is a very simple example of a two-layer neural network. This is not called a deep neural network because we only have one input and one output layer. We don't have any hidden layers, therefore this is just a neural network. This is not a deep neural network, right? So let's recall something now. When we looked at biological neural networks, we said that neurons fire or not, right? They either fire or they don't fire. And this is as much as we can pretty much speculate about the biological neurons, right? Some of them fire, some of them don't fire. They fire through electrical potential, so voltages, and those voltages may vary in magnitude, right? So this right now produces an output between minus infinity and infinity, both of them. Because, I mean, x0 could be infinity, and if x0 could be infinity and this w is greater than 0, then the output will be infinity. If any of them is negative infinity and then the output is also positive, then it could produce minus infinity. And this is not good for defining whether a neuron has fired or not, because how do we define whether a neuron fired or not, or whether a neuron is activated or not? So what do we need for this? We need an activation function. And let's talk about activation functions. So activation functions pretty much are functions that take that output that can be between minus infinity and infinity and give us a meaningful number, a number that can actually tell us whether a neuron fires or not. And this is actually very cool. So let's look at one of the example activation function. This is called the sigmoid activation function. And this is 1 over 1 plus e to the minus x. So this function, if you're not familiar with it, so this function actually takes any inputs, any x input, and produces a number between 0 and 1, which is actually very cool, because now if the output is 0, after this squashification function, how some people call it, then we can interpret that as, well, the neuron didn't fire. If the input is greater than 0, let's say 0.5, then we can say, well, the neuron fired, not all the way, but it fired. And then if the output is 1, then we can say, well, this neuron is lit up all the way. It has fired all the way. Let's actually look at this function in the tool Desmos and see how it looks. Okay, guys, so this is the function, the sigmoid function. And let's look at it right now. So, well, we take one input, and that input is either always it's always a number between 0 and 1. And let's say that the number is the output, this x is 5. So for 5, which is right here, the output is 0.993. Let's say that the output was 2. If the output is 2, okay, well, for 2, the output is 0.881. Let's say that the output is minus 1. So right here, minus 1, right? So for minus 1, the output is 0.269. Let's say that the output is 0. At 0, the output is actually 0.5. So this number takes positive numbers, very positive numbers, and approximate them to 1, and negative numbers approximate them to 0. So the number that is 0, when it's not negative or positive, it's 0, then the output is 0.5. So what can we interpret about this function? Well, if we have a high output, let's say 5,000, then the output will be very, very close to 1. Or 1, right? And when the output is very negative, let's say minus 8, then the output will be close to 0. And this is pretty much a very helpful function, because it can take whatever output we receive from the neuron, and then from there it can tell us, well, this neuron fired a little bit, fired a lot. Maybe if it's 0.5, it fired halfway through. If it's 2, it fired 82%, 88%, I mean. Great, so let's look at other activation functions. So again, this sigmoid activation function outputs a value between 0 and 1. Now this is another function which is very used. This is called the rectified linear unit activation function. So if you're familiar with computer science, then you probably know what this function max outputs. So it says max between 0 and x. Max between 0 and x, which means that whatever number, if it's negative, then the output will be 0. If it's positive, greater than 0, then the output will be x, regardless of what it is. It could be, I don't know, 500. The output will be 500. So this outputs a number between 0 and positive infinity, because now x, whenever x is positive, then the output is x, and x could be infinity, right? In theory. So let's look at a function. Let's look at the graph of this function and see how it looks. Great, so the output of this function is, for any number that is negative, the output is always 0. And for any number that is positive, then the output is just that number that is positive. And as you can see, is a line y equals x after 0, right? This is why this is called a rectified linear unit. So whenever it's positive, you have your line y equals x, and that's pretty much what we have. So this function is useful because it can tell you whether, okay, the neuron fired, or it fired a little bit, it fired a lot, it fired super a lot. If you can, whereas with the sigmoid function, you're restricted to between 0 and 1. With this one, it's between 0 and infinity, which means that a neuron can matter much more in magnitude than other neurons. So if we have an output in the other neuron that is just 1, and then we have an output for another neuron that is 5,000, then you have a great range, a great difference between 1 and 5,000 there, right? So this is why this is a very useful function for activating neurons or determining whether neurons activate or not. So let's look at one more activation function. So another activation function is the tangent activation function. And if you have your trigonometry fresh, then you'll recall that the arctangent or the inverse tangent of x will produce an output that is between minus 90 degrees and 90 degrees. If we turn that into radians, it turns out that that is about between minus 1.5708 and 1.5708. Now this function is not as popular as these two functions, but I just thought I'd mention them just to put it out there. We're not even going to look at the graph of this function, but you know what? In fact, let's look at it because we can look at how smooth this function is. So let's go ahead and look at this function. Great. So if we look at this function, we can see that this function is a little it looks similar to the sigmoid function, but it's like smooth in the sense that it can also produce negative values. And this is actually very cool because now not only can we tell a neuron fired or not, but we can also tell something very interesting, which is whether the output of that neuron actually affects negatively the input or the output, I mean. So now we can tell whether whatever value is this neuron, if it's activated by this activation function, then we can tell, well, maybe this neuron affects the output negatively. Say the output is, are you going out to play? And then the input or the value of this neuron determines whether it's raining. So the more it's raining, the less likely you are to go out and play. So this negative here part could represent that very much, like, okay, well, if it's raining a lot, then maybe you don't want to go out to play. So this negative part here affects negatively the output, which is going out to play. So we also have a positive part here, which is pretty much what can determine whether the neuron fired positively or whether this output of this neuron affects the output positively. Great, guys. So by no means is this a complete summary of all the activation functions out there. There are many more, but I think these are the basics and you guys should at least be familiar with these. Now, how does this apply to our functions that we had before? Because remember, we are representing a network of neurons based on a function of multiple inputs, right? That's for the multi-regression. So if we revisit our equation, all we have to do is apply one of the activation functions, in this case sigmoid, and we'll see that if we apply sigmoid, the output now of this network will always be between 0 and 1. So no matter what inputs we get, we're always gonna get a number between 0 and 1, which is actually very important. So this is an output that represents whether the neuron fired, or if it fired, how much it fired, which is great. So in the next video, we're going to actually go over this whole neural network, and we're going to explore how it works in depth, because in this video we only covered the multiple input function, but it's only one output, and it doesn't have any hidden layers. So how do these hidden layers work? What is the big mystery behind the neural networks? Why do they work so well? I don't know if you know this, but neural networks have actually outperformed humans in many tasks, like facial recognition. They can recognize faces with higher accuracy than humans can. So this is actually very interesting. Let's just go ahead and dive into these neural networks and see why they work so well. So once again, guys, I want to leave you with this thought before I leave. So be curious. I have given you a lot of information about neural networks, something that should immediately trigger something in you and pretty much want to find out a lot about them. Like, this is, at least to me, this is like very interesting. So just be curious a little bit, because when you're curious, you go ahead and you ask questions, you investigate, and you learn a lot more. So the other thing is, ask questions, maybe to yourself, maybe try to think why things work, why they don't work, and maybe ask questions to other people that may know a little bit or may be more familiar with the topic than you. And then try something out. If you have learned some information, then just go into a piece of paper, try to see why it works. Just try something out. Just do something, because just hearing this guy talk all day or whatever, you're gonna learn, but you're gonna forget too. And the point about this is to be able to use this knowledge into the future, no matter when. Use this into the future, and maybe build something that's not even there yet. Maybe you'll build the next general intelligence being. So I want to thank you for watching this video. Once again, my name is Brian. If you have any questions, any thoughts, any ideas, or just like to give your review about this video, please just go ahead and leave a comment. If you like this video, just hit the like button down below. And if you are willing to watch more videos, then just go ahead and click subscribe. Thank you very much, and you have a good day.